Hi, welcome along to our second video about the photoelectric effect. We will be covering the photoelectric effect, but we're going to be really emphasizing this term here, the electron volt. It's going to be a really crucial idea in this area of physics. So to give you a chance of understanding the electron volt, in the introductory unit we talked about 1 volt being 1 joule per coulomb. In other words, it's a measure of the amount. We can express that as an equation, the work done or the energy transferred when an amount of charge Q moves through a voltage V is given by that equation, because this is the number of coulombs and this is the number of joules given to each coulomb. So we're going to apply that to a sort of deceptively simple situation. We're going to imagine a circuit with a break in it, positive side of the battery. So we can imagine an electron making the jump across that gap there, and we're going to make this a 1 volt battery. So the charge, the electron in this case, which is the smallest amount of charge that could move, kind of moves through 1 volt. So how much energy is transferred in that situation? Well, we've got W equals QV. We're going to need to know how much charge an electron has and all the kind of vital data that you need. And I'm assuming I can give you a paper copy of this. We shall see. Is on here, and you can see the magnitude of the charge in an electron. So why has it got that word magnitude? Well, because if it was the actual charge, it would be a minus number. Is 1.6 times 10 to the minus 19 coulombs. So the charge of the electron is 1.6 times 10 to the minus 19, and the voltage, well, I just said that was 1 volt, so the work done is 1.6 times 10 to the minus 19 joules. So assuming there are no energy losses, and if this is a vacuum there wouldn't be, the electron has now got kinetic energy 1.6 times 10 to the minus 19 joules. And that's a special quantity, and it's called an electron volt. So 1 EV, 1 electron volt, is 1.6 times 10 to the minus 19 joules. And physicists love using this because there's a simple relationship here. If you had a 1000 volt power supply, and then you let something with a single charge, like a proton, jump across that gap, its kinetic energy after jumping across the gap would simply be 1000 electron volts. The voltage is the number of electron volts. You need to be able to convert to and from electron volts. So if we ask the question, can you convert 5 electron volts into joules? Well, we've got 5 lots of 1.6 times 10 to the minus 19, or you can just look at that E there. It just says to me 5 times E, so it's 5 times the charge on an electron from the data sheet. I guess we better bung that in our calculator. So it's 5 times 1.6x minus 19 equals 8 times 10 to the minus 19 joules. Of course, you need to be able to go the other way as well. So if I said this object's got this moving object has got kinetic energy 3.7 times 10 to the minus 18 joules, how much kinetic energy has it got in electron volts? Well, we've got to decide how many lots of 1.6 times 10 to the minus 19 will go into that. We've got here 1.6 times 10 to the minus 19, so it's 3.7 times 10 to the minus 18 divided by 1.6 times 10 to the minus 19. So fraction button, 3.78 x minus 18 over 1.6 x minus 19 equals 23.625 electron volts. We're going to round that back for the moment to 24 electron volts. If we were going to use that in a further calculation, with just starting to drip in about significant figures, we would use that accurate figure. But it implies that there was this number here was to 2 significant figures, so we're giving the answer here to 2 significant figures. We'll look at that in more detail in the future. So how does that relate to the photoelectric effect? Well, there are 2 ways. I think possibly the easiest thing to say is that Because these numbers tend to be very small in the photoelectric effect, they're all times around 10 to the minus 19, simply by expressing these two quantities in electron volts, we can have much more manageable numbers. The other reason is that there are experiments where we can measure the kinetic energy of an electron directly via voltage. And I'm just going to describe that situation now. It's not one that you need to know in detail. I'm putting it in here because I think by putting it in here, it will help you get a feel for why we're using this. So we've got our metal surface. We're imagining an electron in the metal surface. It comes along, it absorbs a photon, and then it moves off, and we want to measure how much energy it's got. So we're going to have a metal gauze, like a fine metal mesh, so the photons can come in and then the electrons can hit that. So we're going to need a circuit. We want to make this negative. You'll see why in a moment. We want to be able to measure the voltage. So we probably really need a variable power supply. We need a very sensitive ammeter because that will detect the electrons moving through the circuit. So we're going to imagine, just to kind of put some numbers on it, that this has got an energy of 4 electron volts. It's moving off with an energy of 4 electron volts. So if we set this to 3 volts, will the electron be able to make that jump from there to there? Yes, it will be able to, because it's going to lose energy. It's moving towards the negative side of the battery. But we know that an electron that moved starting from rest across that jump in that direction would gain an energy 3 electron volts. So the energy required to move in that direction is 3 electron volts. It's like the MGH equation. If you need 12 joules to lift a book onto a shelf, then the energy you get back if you move the book from the shelf to the floor is also 12 joules. So in that situation, the electron gets across and we get a reading on the ammeter. What happens if an electron is given out with just 2 electron volts? It hasn't got enough energy to cross the gap. It needed 3 electron volts of energy to cross the gap. And therefore the ammeter reads 0. And so by changing the voltage, we would eventually find a particular voltage reading that would just stop the electrons getting across. So let's imagine that we have an electron released. It's got exactly 2.8 electron volts of energy. If we move that voltage down, we'd see the reading on the ammeter getting smaller and smaller and smaller. And when the current just drops to 0, the voltmeter would read 2.8 volts, and we knew that the electrons emitted had got energy 2.8 electron volts. Right, just remains now to just give you a little bit of practice dealing with electron volts, and we're just going to relate it to kinetic energy, which is something else we did in the introductory unit. And it's not uncommon for questions about the photoelectric effect to expect you to know something about kinetic energy. So the question we're going to ask ourselves, if an electron has energy 2.8 electron volts, how fast must it be going? And I'll do a worked example and then I'll get you to do one. Well, the first thing we need to do is convert that to joules. So it's 2.8 times 1.6 times 10 to the minus 19. 2.8 times 1.6 times 10 to the minus 19 equals, I've got 4.48 times 10 to the minus 19 joules. So 4.48 times 10 to the minus 19 joules is equal to a half mv squared. We can't have two things we don't know, so we're going to need the mass of an electron. Back to our data sheet. Electron rest mass going across 9.11 times 10 to the minus 31 kilograms. So what we're told is 4.48 times 10 to the minus 19 equals a half times 9.11 times 10 to the minus 31 v squared. So we're going to carry on with simplify, then rearrange. 0.5 times 9. I'm just checking I've got that right. Yeah. So that gives us 4.555, writing all the figures down, times 10 to the minus 31, equals 4.48 times 10 to the minus 19 v squared. So v squared is equal to 4.48 times 10 to the minus 19 over 4.555 times 10 to the minus 31. So 4.8. Right, I'm going to do that again with the fraction button. I want you to get into good habits, so I have to be in the same good habits. So that gives us that v squared equals 9.835, and I'm just going to do ... to indicate I've got more figures on my calculator, times 10 to the 11, and then we're just going to do square root answer equals, and we get the velocity. Well, that's quite a big number, quite hard to write down, so I'm just going to press this eng button to put it into kind of standard form, and we get 9.92 times 10 to the 5. Just noticing that I've moved the decimal point 1, 2, so I need to change that number by 2 to indicate it's now times 10 to the 5. Right, I'm going to get you to do one now. So let's say if the kinetic energy of an electron is 10 eV, I want you to stop the video now, go back if you need to, and then find out how fast the electron's going. You got an answer? Good. Let me just do this in a different way now. So we're saying 10E equals a half mv squared. We can move the half across by multiplying both sides by 2. That then disappears. And then we can get v squared divided by dividing by m. So v squared is equal to 2 times 10E over m. So v is the square root of 2 times 10 times 1.6 times 10 to the minus 19 over 9.11 times 10 to the minus 31. It doesn't matter if you did it exactly the same way as me, but my job is to try to cover all the different ways of doing things. Now, this is where a natural display calculator makes so much difference. So we've got on the bottom times 2 times 10 times 1.6, and then on the bottom there we've got 9.11. Okay, again, press the eng button. 1.87 times 10 to the 6, or let's call that two significant figures. 1.9 times 10 to the 6 meters per second. Right. Hope you got all that, and I'll give you some practice questions now. Thank you.